Hello students, welcome back to next session. In this session we are going to discuss about effects of condenser and evaporator pressure on COP. In earlier session we have discussed about the effects of superheating and subcooling of refrigerant. So here the effects of condenser and evaporator pressure is also very important design aspect in refrigerator systems that we shall discuss in detail. As we discussed in earlier sessions, this is the syllabus, and now we are going to discuss about effects of condenser and evaporator pressure on COP. So in next session, we are going to start the multi-pressure system, and before that, I am going to take a small session, and we are going to discuss few problems on condenser and evaporator pressure and its effect on COP. And those problems will be very simple, and you can easily understand those problems. Students, we will discuss in very short session. So effects of condenser and evaporator pressure on COP. The coefficient of performance of COP is a key parameter that determines the efficiency of a refrigeration system. It is defined as refrigeration effect RE divided by work input. So COP of the vapor compression refrigeration system is influenced by evaporator pressure, that is known as PE. So PE is on low pressure side, evaporator is on low pressure side, and condenser is high pressure side. So we know that from cycle and even from the arrangement in the very first class of this unit, we have discussed the evaporator and condenser. So condenser plays a high pressure side, and evaporator is always low pressure side. The evaporator pressure corresponds to the saturation pressure at the refrigerant evaporating temperature. So here it is related to saturation pressure, and a higher evaporator pressure means a higher evaporating temperature, that is TE, while a lower evaporator pressure means the temperature is also lower. So impact on refrigeration effect. So the refrigeration effect RE is the amount of heat absorbed by the refrigerant in the evaporator. Increasing PE, higher TE, so that is increases RE since more heat is absorbed. Decreasing PE, evaporator pressure, so that is low pressure, lower temperature, decreases RE, refrigerating effect, reducing system performance. So impact on work input. The compressor needs to increase the refrigerant pressure from PE to PC. So here higher PE reduces the pressure ratio PC by PE, leading to less work required by the compressor. So lower PE increases the pressure ratio, increasing compressor work. So lower PE is not desirable since it increases the compressor pressure. So a higher PE reduces the pressure ratio, leads to less work required by the compressor. So higher PE is a desirable one, and lower PE is not a desirable one here. So impact on COP. So higher PE, it is higher COP, so that is desirable, higher PE, and less work required for compression, and a higher refrigeration effect. So lower PE is yielding lower COP, and more work required for compressor, and lower refrigeration effect. So lower PE is not desirable. So here increasing evaporator pressure shifts the cycle towards a higher enthalpies at state 1, increasing H1 minus H4. So that is here refrigerating effect. So it also reduces H2 minus H1 compressor work, thereby improving COP. So the COP of refrigeration cycle is given by, so we know this, it is refrigeration effect RE by work done, H2 minus H1 is the work done, and H1 minus H4 is refrigerating effect. And H1 is the enthalpy at evaporator outlet before compression, H4 is enthalpy at expansion valve inlet, and enthalpy at a compressor outlet is H2. So effect of decreasing evaporator pressure on COP. When the evaporator pressure decreases, the following effects are observed. So here, reduction in refrigerating effect. So that is RE. The refrigerant enters the evaporator at a lower pressure and temperature. The enthalpy difference H1 minus H4 decreases, meaning the refrigeration effect per unit mass is lower. So here the enthalpy difference when H1 minus H4 decreases, here the refrigeration effect per unit mass is also becoming lower. This reduces the cooling capacity of the system. So the ultimate refrigeration effect is lower here. Increasing in work done by the compressor, WD, a lower evaporator pressure increases the compression ratio, which is PC by PE. A higher compression ratio leads to more work input required by the compressor. This increases the enthalpy difference H2 minus H1, rising the power consumption. So reduction in COP, since COP is the ratio of refrigeration effect to the to work done, COP equal to H1 minus H4 divided by H2 minus H1, and here a decrease in H1 minus H4 and increase in H2 minus H4 H1 both contribute a significant, so here a significant drop in COP. So that is COP is reduced, and here the system requires more power for less cooling output, reducing overall efficiency. So here this is the system requires more power for less cooling output. So this more power requirement is always non desirable. So here, when you are decreasing the evaporator pressure, having the significant effects on COP. When the evaporator pressure decreases, the following effects are observed. So reduction in refrigerating effect, that is RE. The refrigerant enters the evaporator at a lower pressure and temperature. The enthalpy difference H1 minus H4 decreases, meaning the refrigeration effect per unit mass is lower. So here the entire refrigerating effect is lower. This reduces the cooling capacity of the system, increase in work done by the compressor. So a lower evaporator pressure increases the compression ratio, which is PC by PE. So the higher compression ratio leads to more work input required by the compressor. This increases the enthalpy difference H2 minus H1, rising the power consumption. So these are the effects of evaporator pressure. Next, we move on to the effect of condenser pressure on COP. In vapor compression refrigeration system, VCRS, the coefficient of performance COP is defined as, so it is our standard COP, refrigeration effect by work done, and refrigeration effect is the heat absorbed from the evaporator, and work done is work required by the compressor. The condenser pressure is directly affects the work done by the compressor and on the refrigeration effect, thereby influencing the COP of the system. So the condenser pressure on COP, the condenser pressure PC corresponds to the saturation pressure at the refrigerant condensing temperature. A higher condenser pressure means a higher condensing temperature. Impact on refrigeration effect. The refrigeration effect RE is given by H1 minus H4. So higher PC, higher TC reduces RE as the refrigerant leaves the expansion valve at a lower enthalpy. Lower PC is obviously lower TC, so that is compressor temperature, condenser temperature. It increases RE, so refrigeration effect is getting improved, improves cooling efficiency as well. Impact on work done, the compressor has to raise the refrigerant pressure from PE to PC. So here the higher PC increases the pressure ratio. So pressure ratio, it is also can be called as compression ratio, leading to more work required for compression. Lower PC reduces the pressure ratio, lowering the compressor work. Next is effects on decreasing the condenser pressure. If the condenser pressure decreases, example due to improved heat rejection, lower ambient temperature or effective condenser design, the following benefits are observed. So lower compressor work, since the compression ratio is reduced, the compressor consumes less power. Higher refrigeration effect, more energy is available for cooling, that is the biggest advantage in this, and a higher COP, so performance is also better. Less work is needed for the same cooling effect, leading to increased system efficiency, thus reducing condenser pressure while maintaining the sufficient condensation improves. It improves the COP and system efficiency. So impact on COP, when the PC higher PC, then there is a lower in COP. It is we have seen in earlier slides. More work required for compression and lower refrigeration effect. So lower PC, higher COP. So that is the advantage. And the condenser pressure, when it is lower, the COP is good, less work required for compression, higher refrigeration effect, and increasing condenser pressure shifts the cycle toward lower enthalpies at state 3, reducing H1 minus H4. So it also increases H2 minus H1 compressor work, thereby reducing COP. So now let me consolidate what we have seen in the condenser pressure and the evaporator pressure. So this is what is happening. So you can remember these points so that you can explain very easily in exam also. These are the points we have discussed in this particular session. So here the parameter is refrigeration effect. What is happening in evaporator pressure? Here increased evaporator pressure, the refrigeration effect is increases, and increased condenser pressure. So a refrigeration effect is decreased. So this is a disadvantage and this is advantage. And compressor work is decreases here, and increased condenser pressure increases the compressor work. So this is not advantageous and this is advantageous. And pressure ratio, that is PC by PE, that is decreases in case of increased evaporator pressure, and that is increases in case of increased condenser pressure. So that is COP increases in case of increased evaporator pressure, and COP is decreases when you increase the condenser pressure. So this simple table will make you understand, make you remember this cycle in better way. So please remember these points alone, students, and I have prepared this summary. You can make use of this summary, students. Next, coming to our books, as usual, you can refer this content in CP Aurora book. CP Aurora Refrigeration and Air Conditioning, third edition, and this is the good book for Unit 2. A refrigeration textbook, that is by Rajput. This also you can refer, but more information you can get in CP Aurora. As usual, we can refer Kurmi, and we can also refer this web resources, that is NPTEL and Bright Hub Engineering. But more information, the relevant information you can get in CP Aurora rather than any other references here mentioned here. We stop here, students. In next session, I will have a very short session where we are going to discuss very few problems on this. So we stop here. Thank you, students. Thank you.